Well, thank you to the organisers for inviting me, and thank you all for listening. Hopefully I'm going to go over some stuff here that won't be a massive surprise to anyone, but the kind of aim of it is to make everyone think a little bit differently about how we characterise and benchmark devices, whether that's using benchmarks, designing benchmarks, or just reading about them. So I'm going to go through an introduction to benchmarking just to make sure we're kind of all on the same page with what we mean, and then I'll review the current state of play, which is very, very non-exhaustive. Please don't shout at me if I've not mentioned your favourite benchmark. I've not mentioned all of my own favourite benchmarks. And then I'm going to go through a proposed benchmarking methodology of how I think we can kind of standardise the way we do benchmarking, and back that up with a case study. So we use benchmarks in everyday life all the time. The gold benchmark index is a way of pricing gold. The qualifying times for the Boston Marathon. So these are benchmarks, but they're benchmarks based on your age group and gender. So we're starting to tailor benchmarks. Then we have what is called the fundal height benchmark, which, if any of you have ever had a baby, you might have seen this kind of chart. It measures your fundal height through pregnancy and looks at the baby's expected size and weight. And not only this is tailored by age and gender, it's tailored by your BMI and your race, so it's extremely tailored to individuals. And then we have university entrance grades, the kind of most standard of benchmarks. There is a benchmark that you have to pass to enter this course. So we're used to benchmarks in everyday life, and we're not necessarily used to kind of interrogating them on where they come from or how well they're applied. So the Cambridge Dictionary defines a benchmark as the act of measuring the quality of something by comparing it with something else of an accepted standard. Seems to make sense to us when we look at it like that. Or the use of something as a standard in order to improve your own work, products, or processes. This may be kind of the more typical one we think of when we're looking at quantum computing, but I want to look at the first, more key one and kind of break that down a little bit. So we talk about measuring the quality. What do we mean by quality is the first question. Are we talking just about size of your device? A single gate? Is it experimental? Is it something we can just look at and see? And then there's the of something. What is that something that we want to benchmark? Is it the device? Is it our algorithm, including classical bits? Or some combination of the two? And then the final part of that definition is by comparing it with something else of an accepted standard. Now that bit's really tricky with quantum computing, because what is our accepted standard? Is it a classical alternative processing method? Is it a different quantum processor? Is it our own experiment, but that we did last year? So we need to make sure we've answered all of these questions when we develop a benchmark. So what is the something? This can be hardware, right from an individual qubit level up to a whole device. Or it can be a software, from a whole pipeline, your hybrid quantum classical algorithm. Or it can be, maybe I just want to benchmark a particular choice of parameter or error correction strategy that I'm testing out at the moment. And then there's this kind of fuzzy middle ground, this hardware-software interaction. So maybe something like an embedding algorithm. Maybe you want to benchmark that. We talk about measuring the quality of something. So measuring the quality is what we're going to call characterization, learning about the device. So we typically do this using a fitness function, which can range in complexity from just being a kind of pass-fail metric to a single numbered measurement, so gate fidelity, to a really complex functional energy landscape about how something behaves compared to a range of parameters. And then we have to define our characterization methodology. So if your what is hardware, your software should be something you know and trust. It's all about which bits do we control and which bits are we testing. And by going through this process of thinking about it, you're much more likely to catch things that you should control for that maybe you weren't. And the final question is, what is our accepted standard? So is your accepted standard absolutely perfect performance? You want 100% fidelity, which is kind of a binary pass-fail. Or is your accepted standard your classical results or your simulated results? Or is it results from a different quantum device entirely? That could be a different annealer or comparing it to the best known circuit model device. Or are we looking at previous results from the same device, maybe with a different parameter or a slightly different change in conditions? So now I'm going to go through some of the benchmarks that are in use currently. These are not all specifically quantum annealing benchmarks, but I think raise some of the points that come across all quantum computing. So we talk about characterizing quantum devices, and we can do this on a single qubit level or on a whole device level. And the kind of easiest, simplest ones for us to quote are the things that are designed or measured by the manufacturers. So the number of qubits, your gate fidelities, decoherence times and readout fidelities. These are all things that might come up on the very first page when you open D-Wave IBM's website. These are the numbers we're likely to read out, which is a really useful first step. It can give us a first glance of what that device may be like to use. But it's not really enough for full characterization. For example, how does gate fidelity change when we're running multiple gates in parallel? We know that typically fidelity degrades. This could be due to crosstalk or in problems addressing individual qubits. And it's only when you start to kind of dig into these numbers that you realize, well, maybe we need to do some further characterization. The quantum annealing single qubit assessment was a really interesting study by the Los Alamos Research Group a couple of years ago, where they measure for each individual qubit in a quantum annealing device these 4 parameters. And they do that by looking for deviations from a classical Gibbs relationship, and then when they plot that out, they can extract these 4 parameters. And they found that there's actually lots of variations within a qubit chip. There are regions of different performance, and in fact, qubits that are oriented horizontally versus vertically behave very differently. And that's really interesting because it tells us a little bit more about how that device performs. Not that device as a product sold by the manufacturer, but my device that I've got in front of me. And, you know, we're not in that stage of quantum computing yet where everything's just kind of factory line produced and we can guarantee that my D-Wave is going to be exactly the same as your D-Wave, and this proves that. And that's interesting, but it's not, again, it's not really a full story because it's hard intuitively to look at these 4 parameters and immediately see how that might affect our results when we're doing something that we actually really care about. So we're now looking at whole device level characterizations, and quantum volume was proposed by IBM in 2018 with a principle of quantifying a quantum computer's power with a single parameter based on the question, can this device run a given algorithm? It's pretty simple. It's based on the number of qubits, which is easy, and an achievable circuit depth, which is a little bit harder to calculate because it takes into account a number of things such as connectivity, decoherence, and parallel performance. But it's an interesting metric because it gives us a kind of one number comparing devices against each other, and there are a number of papers that compare a range of devices that are on the market now. And it's useful, again, but when we compare different devices, even using a metric like this, there'll be lots of parameter choices that we're making that we're maybe not considering. Do we use the embedding strategy suggested by that manufacturer, or do we use the embedding strategy as a constant throughout the whole experiment, and how does that affect our results? Another issue with this is it's not very clear at all how it translates to quantum annealing or things like topological quantum computation. People have kind of tried to find equivalents, looking at equivalent problems that these computers can solve, but then I think you're getting into a whole different kind of benchmarking strategy. Another way of characterizing devices is mirror circuits. So randomized mirror circuits are a randomized sequence of gates followed by their exact inversion. And this is a really interesting way of characterizing quantum devices because we can control inputs and therefore expected outputs. We can use mirror circuits to show how performance scales with circuit width and depth. These have been used a lot in gate model quantum computing, but again, there are some issues with them being used to show performance against real-world applications. Because in the real world, most quantum algorithms don't appear to be a random sequence of gates. They're actually often repeated chunks of gates performing known sections of algorithms. So maybe, although a randomized mirror circuit is very general, maybe you're giving up some usability for generalizability. And that's fine if your aim is to be very general, but this is something we've got to think about as we're doing it. And then the opposite end of the spectrum is really the application-driven benchmarks. Two examples are the Q-score and the supermark suite, which tend to be benchmarks that rely on performing a given algorithm. And things like the supermark suite actually have a suite of common algorithms, including ones with error correction, that you can test your device against. And they kind of encourage you to publicize your results and compare them against other devices or other ways of doing things. And these are really useful because they actually take into account the entire pipeline. They're probably the closest thing you can get to testing a device on something that's useful, on getting a number that represents how your device might perform for your application. But what you lose here is the distinction between classical and quantum improvements, and any distinction about what area is causing your improvement or degradation. By looking at the application as a whole, you get a very useful number when considering a similar application, but what do you know about the device itself and how it's performing? We can also benchmark based on time to solution. So this was a piece of work that I did in the spring when looking at using a quantum annealer to train a sparse Boltzmann machine. But we were mainly concerned about the time taken. And you can break the time taken to train a sparse Boltzmann machine into these sections in the chart, and the loops show you how many times you might have to perform each step, which turns out to be quite a lot. And we were actually getting our QPU performing significantly slower than our CPU alternative. But actually, when you broke it down, we found that a lot of that time was spent in the internet latency and the queuing phases, because you have to run this loop so many times. You can't feed in all your data at once. You have to feed in every piece of training data individually in every epoch, which means those latency times really add up. So we defined the concept of a local QPU, which considered if we had one on our desk that we could solve the I/O problems for. And by breaking this down and comparing it to our actual results, we start to see how much of an issue that the I/O problem is. And by narrowing down what the problem is, we can better benchmark the different stages of our process. So that all sounds like I'm being really, really negative. Like, all of these benchmarks are really good and they're really useful in telling us things about our devices. But what's often really tricky is that when people complete benchmarks or write about benchmarks, they don't often explain exactly how they've come to that decision and all of the parameters they've chosen in the way. So I want to propose a bit of a framework in which anybody, so that would be a user, a developer, or a researcher, can form a benchmark in a way that defines, articulates, and justifies their success criteria, their benchmarks, and their resulting claims. And this is kind of a 5-step process, which starts with 2 questions you have to ask yourself about your purpose and your objective function. And then there are 3 further considerations of generalizability, robustness, and expressivity. And this is all held together in the middle by documentation. Because fundamentally, if you found a benchmark that works for you and your purpose, that's great and that's all you need. But if we want anyone else to be able to use it, we need to make sure we've well documented exactly what we've done. So these 2 questions. Your first is purpose. What is the main purpose of your intended success metric? And these are some options for you. You can have something else if you want, but from my reading and my own use, these are kind of 5 of the most typical, of comparing different architectures or different chips, even comparing the relative difficulty of problems, monitoring your error correction. So once you've really nailed down what your purpose is, you should have a head start in answering question 2 of how do you define a successful quantum computer? And again, I've suggested some options where A, I guess, is the easiest to answer, the best or most of a desired metric, in which case you can do some Googling, get some spec sheets, and probably just pick the one that you like. Or we can get more complicated than that, and we can talk about whether it executes the process it was programmed to do. That's kind of tricky to measure, as we know through quantum devices. So we can do things that are to do with simulation. So do we care that it produces a state that matches simulation? Or maybe we don't care about the exact state it produces. Maybe we just care that the probability distribution that comes out at the end matches the simulation. Or maybe we're just real pragmatists and we just care that the result that comes out is useful. And by useful, we mean, is it better than we can get classically? Or can we just get it faster? So once you've defined these two things, you should have a good idea of what your benchmark should consist of. And now we have to consider these three extra factors. So generalizability. How generalizable do you want your benchmark to be? So what information will my benchmark give me on other operations? Have I picked something so specific and so niche that although it's great for me, maybe it's not that useful for anyone else, or maybe it's not even that useful for me in 4 weeks' time. But if I go the other way and I make my benchmark too general, have I lost the purpose of doing it? Does it now not tell me anything about the thing that I care about? So things like randomized circuits are very, very general, but they're often not incredibly useful because our circuits aren't made like that. So we can do randomized circuits, but with some level of structure, where the randomized elements are based on elements that we know appear in typical problems. Robustness. So, do the key conclusions from my benchmark change with increased noise or a change in parameters? If I change an embedding, say, does my benchmark now fall apart? Are my results not valid? And if so, does that tell me something about the embedding that I've chosen? So the example here, do you want to compare Olympic gymnast Simone Biles with Olympic swimmer Michael Phelps based on their overall medal hauls or on their 100-meter butterfly times? Do we want to compare like for like in a situation, which I suppose is typically the way we're kind of taught to do the scientific method? You want two things as close as possible to compare? Or is it actually more useful to compare a best for best scenario? Maybe one embedding algorithm works really well on one device, but not necessarily on my other one. And the last factor is expressivity. So what is the difference in results between a really bad device and a really good device? If I pick a problem that's really easy and all of my devices are giving performance of above 95%, say, am I really learning anything about the difference between those devices? And actually, when I then apply it to my real, probably harder problem, we then could realize that actually these devices are showing a great range of results and it matters a lot which one I pick. So we can use functions to define how demanding a problem is. So the reference there uses a particular numeric value on a problem, where at one end of the scale, a 50-50 coin toss would give you the answer, and on the other end, we're at problems where we can optimize towards, but we're unlikely to give a solution. And we can use that to try and pick something where our devices or algorithms in question would be suitably expressive for us. So, hopefully, that methodology made sense, but as with methodologies, it's much easier to explain them if you've got a problem and a scenario to work around. So, as an example, let's say that I want to develop an algorithm to form image classification for medical purposes. I've done my algorithm development on my one device, but before going much further, I want to decide which device gives me the best performance. I know that I require a gate model, but other than that, I have no restrictions in terms of access or what kind of physical qubits I need. So my question is, I need a benchmark. What can I do to determine which quantum device I want to use going forward. So I'm going to answer my first questions. What is the purpose of my benchmark? I'm going to go with option A in this, which is to compare different architectures and implementations of gate model computing. And I've got a number of options to pick from, so I can choose that as my purpose. I might also have a secondary purpose, which could be to compare alternative chips of these devices, if I want to go that far, but primarily my purpose is to compare different chips and architectures. My objective function, to me, I'm a pragmatist. I only care really about my problem, and success to me means that I get a useful result to my problem. My device running my algorithm can classify medical images into 2 classes, say. And that's fine. So my objective function needs to be something that defines whether I've got a useful result to my problem. So I'm going to define my objective function. And if any of you have done much machine learning image classification before, this will all be really familiar. I'm going to use an F1 score, which is a single number calculated from the harmonic mean of precision and recall. And how we get to that is kind of defined along the bottom. So you start with this Punnett square of your labeled data, your actual results, and then what your algorithm has predicted. And you end up with true positives, false negatives, and true negatives. You plug those two into the middle equations to get precision and recall, and then those into the third to get the F1 score. F1 scores are used a lot in machine learning, where you've got an imbalance of the number of true and false cases. And I think that's quite likely in my scenario for medical images, where I might be screening a large population for a relatively rare condition. So we know we're going to have that imbalance of cases. So an F1 score seems like a pretty good idea to me. If I do also care about the actual kind of quantum process behind it, I could introduce a 2-dimensional objective function where on one axis I have this F1 score, but on a second axis I have something like 2-qubit gate fidelity, because maybe I use a lot of 2-qubit gates in my algorithm, and therefore a measure of that gate fidelity would hopefully be indicative of my performance overall. So now I've got an objective function, I have a purpose, and I have to consider my 3 other things. So, generalizability. I am a developer of this algorithm specifically. I'm not a generic researcher in this scenario, I guess. So I'm not really concerned with how my results generalize to other problems. But I am concerned with how my results of my benchmark generalize to my problem. So my problem set are 8-bit grayscale images that are 2000 by 2000 pixels, so they're square images, and I have approximately 1 in 10 true cases. And as we know, 2000 by 2000 pixels per image is a little bit out of the range of what we can do on our quantum devices right now. So I just want to pick a problem set that maybe has the other 2 factors nailed on, but maybe we just say that it's a square image in this case. So we want to make sure our benchmark data generalizes to our problem, but we're not too worried about generalizability further than that. Robustness. So my algorithm requires some sort of embedding, but importantly I want to test the devices, but not the algorithm. My aim here, as I set out at the beginning, was to test the algorithm, my algorithm that I've developed, not the devices or the embedding strategies. So I've decided I'm going to use the manufacturer's recommended embedding tool for each device. Now, I don't know for certain that that is going to be the very best embedding, but that's not the thing I'm testing right now. I want to test how the device performs according to manufacturer's guidance on my algorithm. So now I'm comparing the best, or at least the best known scenario for each device. My algorithm also requires a certain amount of parameter selection, and in my development so far I've determined some optimal parameters for the device that I'm using. So I'm going to use the best values from this initial research and keep these constant throughout. In a kind of much larger experiment, maybe I would optimize each parameter for each device, but we always have to be aware that maybe the ideal case isn't the case that we can do due to time or resource allocation. So I'm going to use the best values for my initial research and keep these constant, and assume that these are unlikely to affect the comparative performance on each device, because the parameters are for my algorithm, they're not in the running of the device. But I am going to record this as an assumption, so that when anybody else reads this, they know that I've chosen this, and that if they want to take this further and optimize these parameters, they may well get better results. My expressivity. I need to make my problem hard enough to show sufficient variation in my devices. So in medical images, let's say scan images, there will be significant variation, but they won't be we know that there's some structure to them. So we can add variation in the training set. We can do this in a typical machine learning way by rotating, stretching, flipping, adding edge cases and artificial noise. But we also know that images with more pixels likely have more natural variations. So we want to choose the biggest image size that we can that our quantum device will still be able to process. So we also need to be aware then, if we're using the biggest device we can, we're likely to need more qubits, which increases the need for swap gates and the higher likelihood for gate errors from crosstalk and stuff. So making sure that as we've worked through all of these things designing our benchmark, we're being aware of every implication that our choices may have. And we can use publicly available datasets. So we might be able to infer relative difficulty based on other published works. So typically for publicly available datasets, there is then a ream of published results on how they perform, maybe on classical algorithms, but it might just tell us, well, this test set compared to this test set, this one looks slightly harder. So maybe that's too hard for our device, or this one looks slightly easier. So we can actually start to be really selective with how we pick our data sets. So I've picked some cats and dogs, because as we know, the internet is full of cats and dogs. And this is a publicly available data set of 30,000 pictures of cats and dogs scraped from Google and Instagram. So we know that there's going to be considerable variations with the classes. And they fit our bill, they are 8-bit grayscale and are square in dimension. The original dataset has 15,000 images per class, but as we know, we want this imbalance of true-false cases. So we can down select to our desired 1 in 10 ratio of true to false or cats versus dogs, depending on your preference, I guess, which one you want to look at more. So hopefully, what that shows is that everything you do, every time you want to benchmark or want to characterize, there are so many tiny decisions that you make that will all impact what your results will mean both to you in the future, and to other people. And that it's a really challenging problem, and it's important to do it in a way that is repeatable and well explained. So by having a model that takes you through the questions that need to be asked and making sure you record your answers to them, hopefully we can get to a place where actually we're starting to kind of cohere the field and make the maximum utility and get quantum computing to the place that it wants to be and needs to be as fast as we can. I'm happy to take any questions.
Thank you, Jessica. So, perhaps unsurprisingly, Kathy gets the first question.
Well, thank you. That was a really great talk, and I really brought together all the different concerns and considerations. I say this because benchmarking is in my job title, so it's the only thing I think about, really. And one thing I think it's implicit in your talk, but you didn't exactly say it, was the approach you ended up taking in your case study was really borrowing from classical benchmarking, the kinds of problems you chose and things like that. And so I guess one question is, would you agree that there's a component of being aware of what's already out there and thinking about how to adapt it to the quantum scenario more than, starting fresh with everything.
Yeah, I mean, it's interesting. I've come from this approach because that's my background, I guess. So it seems natural from me, and I don't necessarily think that. I think if we can do without starting from scratch, that's helpful, and there's a lot of lessons learned. We've also can learn a lot of lessons about bad benchmarking from classical machine learning. So it's important we take those on, but we also need to be aware that at digital computing now, we have abstracted away from the hardware so much. Most machine learning scientists will have no idea how a transistor works. They don't need to. That's fine. We've got to the point where we're kind of happy with how the hardware works. We're not there yet with this, so I feel like if we start to borrow blindly, then we'll miss out on learning much more about the fundamental hardware underneath.
Can I ask a follow-up question?
Yeah, sure.
Yeah, I guess the second part was your point about, you said you did a study of a time to solution where you found you really had to break down the time components. I'm giving a talk later today about where this could have been the introductory slides to it in terms of why are you doing it this way? But one thing we've found is that with quantum annealing in particular, you're studying both the algorithm that's implemented on the hardware, and you can't separate the two. You can't, there's no way to separate the measurement of the device from the measurement of the algorithm. In that case, you can't take one algorithm and map it to the 10 different architectures you have or something like that, which you can do in classical and which you can do in gate model. And so yeah, I think in this particular case where you're stuck with a particular algorithm implemented on particular hardware, you have to use this approach of separating the different components of the time and doing your best to try to understand, is it the algorithm or is it the system that it's running on that is showing me these results. So
Yeah,
I think that's really important in this case.
And our conclusion to that and our follow-up work is that you need to have your hardware in mind when you're picking your algorithm. Looking back, is the Boltzmann machine what we want to be doing because of this kind of repeated sampling thing? Or do we want to look at something like reservoir computing, which is more of a one-shot approach?
So my question was, do you have a paper about that?
It should be coming out soon.
Great, thank you.
Any other questions? I have a question. I mean, this is well outside my area of expertise. Let me preface my question with that. But I'm of course aware that there is lots of demonstrations of quantum advantage, quantum supremacy, call it what you will, thinking about both on main or randomized circuits. Is that useful? And if so, what is it useful for?
It's that really tricky thing about it's useful because it can help get quantum computing the attention and the funding that it deserves, but it can also get us in trouble when we've not documented things as well as we should. Yeah, it's definitely a double-edged sword. I think it's useful, and it's useful to have this kind of buzz around advantage and supremacy, and there are lots of different ways of defining advantage and supremacy. So it comes back to that documentation piece. If we can define it well and your conclusions match your definition, then no one can argue with it. But if you fail to provide that definition in the first place, you're opening yourself up to a lot of disagreement.
Good, thanks. Yeah, there's another question here from Marcin.
Thanks, Paul, and thanks for getting my name right. That almost doesn't happen. It's more of a comment than a question. So, come from a big company, and I can tell you that nobody reads documentation. Just give them something, they just want to run with it.
Yeah.
what can we do about it? Because I think perhaps one of the criteria should be simplicity, but then nothing that we do is simple. Do you have any thoughts on that?
I think no one wants to read documentation. I fully agree with that. Until something goes wrong, and then maybe everyone then goes back to work out where the issue is. So I think in our documentation, it's important to be clear. It's important to kind of articulate things in as simple a way as possible, and actually making sure that the evidence that's in the documentation matches the kind of flashy headline of whatever it is you're pulling out. A lot of people will, you like a title and an abstract and maybe an image. So making sure we're really clear with how that actually matches the documentation that we provide, even if people choose not to read it.
Let's hope. Thanks.
Any further questions for Jessica? Yeah, one at the back there. Yeah.
Yeah, thank you very much, Jessica. For the first example that you showed about the age effect of getting it from like qubit biases and so on, right? So you can also use that to improve further using the device in the future, right? If you learn like something about the noise in particular. So where would this aspect be in your 5-piece model?
In terms of if you're using previous...
If you use the result of the benchmarks to maybe change the way you use the device in the future, maybe if apply some as a calibration maybe.
So I think that's kind of the next stage to the benchmark. You will use the benchmark, and then I suppose it's is this a benchmark because it's just, okay, it's told us something, we've learned it, we've retained it, or is it a benchmark that then goes on to inform how we develop stuff in the future? And that comes into what's your purpose of your benchmark. So I suppose that's your answer to question one is,
oh yes, yes.
We're picking a benchmark that will mean we'll make better decisions or make better designs in the future.
Okay, yeah, very clear, thank you.
If I may just add that in my opinion, that is the real value of quantum supremacy, quantum advantage, and possibly nothing else, is it's a feedback mechanism that allows specialists to improve. There, I said my thing. Good. I don't see any more questions, so let's thank Jessica one more time. Very interesting talk. Thank you. Just a quick announcement. I believe